Hello, my name is Becca Bonham Carter, and I'm an embedded software engineer for a Canadian company called Mission Control. We're a space exploration and robotics company with a focus on software and mission operations. I'm speaking as part of the Flight Software Workshop this year about how we can enable space missions and planetary exploration using deep learning and how we may accelerate the process of adopting these algorithms on spacecraft. I'll begin today by highlighting the lunar mission on which our software is flying. From there, I'll give some brief background on deep learning and deep learning in the space domain in particular. Next, I'll describe some of the challenges and principles we've been considering for designing deep learning solutions for space before moving to discuss flight software for deep learning on board spacecraft. I'll highlight some of the existing flight demonstrations, some key challenges for developing this kind of flight software, and outline our team's current approach to deploying deep learning algorithms on spacecraft hardware. I'll end my presentation by describing two flight demonstrations of our deep learning software occurring this year, and wrap up looking at what we see as the next steps for this area and for our team. I wanted to start here with some of the launch images for the iSpace Hakuto R lander mission. The software and design approaches I will discuss today, including the deep neural network developed by our team called MoonNet, are somewhere in both of these images. This is the first commercial mission to launch to the moon and is currently looping back along this blue trajectory on the slide from deeper space towards the moon's orbit around the Earth. The launch occurred in December last year and is headed for the Atlas crater on the lunar surface. Payloads on the lander include 2 rovers and MoonNet, our deep neural network for pixel-level classification of lunar terrain, which our team trained and deployed on a Xiphos Q7 system on a chip. Right now, MoonNet is on its way to the moon as part of the Lunar AI Capability Demo in conjunction with the Emirates Lunar Mission. We acknowledge the support of the Canadian Space Agency for our lunar surface demonstration. The focus of my presentation today is the workflows and tools that allowed us to train a model to perform inference on another planetary surface and to deploy it on heritage spacecraft hardware. First, since I'm assuming no background in deep learning for today's presentation, I'll take a moment to introduce deep learning and the current state of the field. In the last 2 decades, machine learning has become dominated by statistical models called deep neural networks, or DNNs. A DNN refers to a model which consists of many simple, linear, and nonlinear functions composed together, called layers. The deep part is the number of model parameters to fit amongst these layers, which is typically on the order of 1 million to 10 billion. The most common architecture is a convolutional neural network, or CNN, which is a network in which the functions for most layers can be described as convolutions. The last decade has seen fast development in model architectures beyond the classical convolutional neural network. These architectural advances, along with exploding dataset sizes for common AI applications, have led to consistent increases in inference performance, with deep learning outperforming classical machine learning algorithms across many domains. The range of applications for deep learning has also exploded, from the traditional object detection tasks to natural language processing, anomaly detection, text-to-image generation, and more. However, this wide range of applications comes with risks, with deep learning inherently, or due to privacy and ethics issues with training data, not being the appropriate solution for all problems. There are serious issues of interpretability, ethics, and risk tolerance that make some applications dangerous or inappropriate for deep learning. These issues become particularly challenging in domains with low risk tolerance, like space. Some of these challenges are being alleviated by slower but steady advances in deep learning theory in the form of statistical guarantees, tooling, standards, ethics, and legislation, as well as higher quality training and test data. In the space domain, these challenges pose a particular barrier, but the potential gains from leveraging deep learning have been sufficient to motivate the current active research field we see and an advancing era of deployments of deep learning for space applications. Current and emerging Earth observation satellite systems are using deep learning to enable autonomy, though almost all so far use deep learning inference on the ground segment only. One recent and exciting approach of on-ground deep learning is Horus, a deep learning solution first developed by the Frontier Development Labs and further by the authors of this article for denoising permanently shadowed regions in images taken by NASA's Lunar Reconnaissance Orbiter. The barriers to deep learning on the ground segment versus in flight are lower due to less risk in avoiding the development effort required to deploy deep learning on spacecraft hardware. But while downstream AI is valuable for providing actionable intelligence solutions to customers, moving this processing on board accelerates the speed at which the intelligence is obtained, while also offering the option to only downlink relevant information. Providing actionable intelligence quickly is of high value in disaster, emergency, and security response scenarios, while eliminating the need to downlink the large volumes of data generated on board, save costs, and bandwidth. Looking forward, we see a marked emerging need for more complex operations on board spacecraft. One example is the increased autonomous capabilities planned for the Canadarm3 on the Lunar Gateway. Another is the autonomous navigation and driving planned for ESA's HERA mission to the DART-impacted Dimorphos asteroid. The most promising applications we see for deep neural networks in space are related to communication efficiency and onboard and on-ground analysis and decision-making. There are a number of design considerations we see as steps toward creating effective deep learning-based systems for solving problems in space. One must first successfully differentiate between applications where deep learning is the best solution and where it is not. Then, for those identified applications, we need good pipelines for training and using deep learning models that are accessible and help users to build trust in the systems. This need feeds into the next step, which is to ensure that data products from these deep learning systems prioritize user interpretability. Finally, there is a need for more standardized practices to meet the level of verification required for space applications, and particularly those that are mission critical. There are barriers to overcome to achieving this goal of effective use of deep learning in space, but from our perspective, there are also clear paths to reducing these barriers. The first key principle we see is accessibility, making it easier to adopt deep learning algorithms in an informed manner. Documentation to increase transparency, interpretability, and operator trust is one of the focuses in our ML operations for this reason. Model cards, such as this one for our MoonNet model shown here on the slide, succinctly summarize the intended use case, pitfalls, and key ethical considerations of each trained neural network. These cards are a tool that our team has found useful for increasing accessibility of our deep learning solutions for users and developers alike. Hand in hand with documentation, increased standardization of each step of the MLOps pipeline, from problem identification, model training, and deployment, is needed to better quantify risk and verify these systems for use on mission-critical hardware and applications. There are emerging best practices and suggested standards that are promising, such as one recent proposal for machine learning specific technology readiness levels. There are also existing best practices for space software and systems engineering that, though some adaptation is needed for the specific risks associated with deep learning, do provide concrete guidance on how we can create deep learning solutions for space. There are lessons to learn from a number of sources about building deep learning pipelines for space and successfully identifying applications where they are the best solution. One is terrestrial domains with similarly low risk tolerance, such as medicine. Another key learning and testing opportunity comes from Earth observation satellites. Finally, as with many other technologies for space missions, science specialists and analog missions provide immeasurable value for shaping solutions. The processes and software tools, as well as the neural network model design for the deep learning solutions that our team has deployed on the 2 flight demonstrations that I'll talk about today, were all shaped in part by the lessons we learned during Sandy. a NASA P-STAR-funded 2-season analog field deployment conducted in collaboration with NASA, Texas A&M, and the other partners on this slide. I was on the SANDI 2021 team, working for a month in Iceland with our neural network-based autonomy systems directly alongside planetary geologists. We learned that deep learning data products have to be designed with your users, in this case, the planetary geologists and rover operators, ideally in a continuous feedback loop, in order for the users to actually benefit from the products throughout the mission. Scientists also need outputs so that they can understand and interpret, which emphasize the importance of documentation and derived data products from the neural networks, which were more interpretable than the raw network outputs. The final lesson was that opportunistic science and operations efficiencies emerge naturally from automation. These lessons are not all specific to deep learning, but the nature of neural network model training, selection, and inference makes them relevant to a new and elevated degree. In the last 5 years, there has been an acceleration of research into deploying deep learning on spacecraft hardware for onboard inference. But so far, few missions have been realized with deployed DNNs on board. And as far as we're aware, there are none yet that use DNNs for mission-critical tasks. ESA's PhiSat and OPSAT Earth orbiting satellites are two important examples of spacecraft featuring demonstrations of onboard inference with CNNs. PhiSat 1 and 2 feature a Movidius VPU processor well suited for neural network deployment. Whereas the neural networks on OPSAT are deployed mostly on the CPU, the platform also has a Cyclone 5 FPGA that experimenters can make use of, as we'll talk about later in this presentation. The gap between research and deployments is indicative of the particular challenges for deep learning in this domain. Two interrelated issues are the risk tolerance of space missions and the difficulty with risk quantification for statistical techniques like deep learning. As I've touched on already, methods are needed to increase interpretability of neural network outputs in order to make them useful for mission scientists and operators. The availability of datasets is another key concern. For many planetary and deep space applications, there simply doesn't exist the data needed to train supervised neural networks. This necessitates the use of unsupervised or semi-supervised approaches, or more complex training techniques such as few-shot or transfer learning. Finally, spacecraft hardware requires careful design for power and memory management. That is a particular challenge for large models, huge models, like deep neural networks. The gap between research and deployments is also indicative of the particular challenges to deployment on spacecraft hardware. We see two key challenge areas. The first is that existing hardware for deploying neural networks on embedded devices comes with a number of barriers to using these tools on spacecraft hardware. There's currently more emphasis on tool design for large-scale, massive compute, server-type applications, as well as the barrier of vendor locking of tools and hardware. And from my own experience, a lack of support for custom small devices and networks. The second challenge area is the wide range of hardware constraints we see for spacecraft. Spacecraft hardware comes with, for example, the need for radiation hardening, low power and memory resources, and minimal software architectures with tighter constraints on the dependencies and operations permitted. These two types of challenges featured in both of the neural network deployments by our team in flight this year and are ubiquitous in the field. Main principles of our approach to the MLOps pipeline, as illustrated at a very high level in this diagram here, are twofold. The first is that we have scientists and mission experts in the loop at all stages of the pipeline. And the second is to prioritize making our software tools for neural network deployment reusable. Making these tools more reusable between projects and missions can be promoted by focusing not on the generalization of these naturally custom processes, but on creating and following more standardized practices and leveraging parameterization of what is a central modular pipeline. Narrowing in beyond the complete pipeline, the task of deploying DNNs on a spacecraft is a challenging problem in its own right. Originating as a solution for tackling the deployment problems our team has faced, we've developed a neural network deployment toolkit. The set of tools is dominated by a compiler and runtime for inference that I will now introduce in some more detail. The core of the toolkit is this multi-stage NNEF compiler and a hardware customizable runtime. NNEF is an open source model representation standard from the Khronos group that is well specified and stable. Bringing all models to the NNEF format as a pre-compilation step allows us to support the state-of-the-art models being developed in high-level frameworks like TensorFlow and PyTorch without duplicating development effort due to differences between framework operations and high maintenance costs from the more rapidly changing code bases. The runtime is accessible through a C API and currently supports execution on CPU and FPGA. It also has an architecture which we've designed to support making customization for different OSs, vendors, and hardware. Our goal with these deployment tools is to strike the balance between keeping up with state-of-the-art neural network models, developer effort, code lifetimes, and standardization. We have 2 flight demonstrations this year of our team's deep learning approach, including this deployment toolkit. Our OPSAT experiment, shown on the bottom of the slide here, allows our team to build more experience and test different neural network hardware implementations in flight. While MoonNet, the first use of deep learning on the lunar surface, is a demonstration of our entire machine learning operations pipeline. We are excited to continue iterating on this pipeline and our software tools as the data and the feedback from scientists and operators comes in. The Spacefarer AI Deployment Toolkit is the core development contribution for our OPSAT experiment. The goal of our experiment is to take an existing trained CNN model called SmartCam, which is currently deployed on a CPU on board the OPSAT satellite, and redeploy it as a hybrid CPU FPGA implementation. The SmartCam model classifies images taken by the satellite camera as edge, earth, or bad, where bad indicates not to bother downlinking the image. Our approach for the hybrid deployment was to analyze the SmartCam layers and select those with the potential for the highest performance gains if implemented on the FPGA, and then do exactly that. For MoonNet, our team is leveraging the entire pipeline, beginning from problem identification, model selection, dataset generation, and training. Training of a model for inference on the lunar surface carries the challenge of the lack of data available from the target environment. To alleviate this barrier, we used analog data to supplement open source lunar datasets, including features we could curate using our indoor Moonyard facility with customizable craters, rocks, lighting, and simulated regolith. This allowed us to create the terrain class distribution we expect to see in the Mare Frigoris region surrounding the Atlas crater landing site. It's highlighted at the top of this presentation. MoonNet is a deep learning model deployed on a Xiphos Q7 system on a chip, currently on its way to the lunar surface. Once landed, MoonNet will be used to automate the segmentation of rover images into key geological features of lunar terrain, as illustrated here on some images from our Moonyard. The network will be run both on board the lunar surface and back here on Earth. These segmentation masks and other deep learning data products can facilitate more complex onboard autonomous analysis and operations, such as automated science target selection, mapping and navigation, selective image compression and downlink, crater counts, and tracking distribution, terrain features in each explored region. Up next, we see many opportunities for deep learning to facilitate increased autonomy and efficiency for lunar operations and communication, navigation and mapping, Earth observation and remote sensing, on-orbit robotics, and beyond. Our team is excited to share that we will be commencing beta testing the Spacefarer AI Deployment Toolkit in near term, including the compiler and runtime for neural networks on space hardware highlighted today. We have plans for more product development and deployments in the near term, with our AI team focusing on iterating the tools and approaches I've talked about today. Ending with a little more about our team. We're a Canadian company based in Ottawa, where our office includes our indoor Moonyard analog testbed and a rover and robotic arm test facility. Our key flight contributions this and last year are listed on the right, highlighting our OPSAT and lunar demo involvement. Please feel free to contact us if you have any questions or feature requests for the tools I've described today. Input from the flight software community is always welcome. Or reach out if you're just interested to learn more about the Mission Control team and our work. Check out a demo of the Spacefarer AI Deployment Toolkit at the Flight Software Workshop this year by my colleague Luis, and stay tuned for the first demonstration of deep learning on the lunar surface with MoonMet. Thank you for your attention today for my presentation.